Oh, okay.
Okay, that's where we stop. We got a few slides left, then we can solve the question. Right, you need to know conservation energy and then know how to, in different type of situation, know how to apply the principle of conservation energy. Like in this case, what's the problem? Right, you have a object move up a rough slope at constant speed by a force F and a distance x. Right? Draw a picture. There's a distance x increased by a height h. There's the weight of the object. There's the force applied to the object. So you should be able to write the equation up. Right? Conservation energy, work done by the force. There's the force that does the work. That does the work. Where does the work go to? Friction. Work done against friction. Right? Don't be surprised with the angle or the slope there. Just write the conservation. Then where does the energy go to? The other one is gain in potential energy. Kinetic energy is constant, so you don't have to worry about it. Then write in the equation formula, Fx equals to small f times x plus mgh. Energy input, Fx. Energy output, mgh. Wasted energy is Fx. So efficiency is mgh over Fx. Can? Okay, collision. In collision, we hear sound and cars are smashed up. The energy transformation, in this case, kinetic energy of the moving cars is transformed into sound. Work done in deforming the cars. Energy of the cars and tires. Right? There's going to be friction there. And you touch the tire will be warm. That's internal energy or heat energy. How does kinetic energy
Can I ask something?
Say again.
Can I ask something?
Graph.
Can I ask something? I thought
Go ahead.
deformation is chapter 6.
Deformation, you do work to smash up the parts, the car, bonnet, or whatever is smashed up. That's work done, no? Like in this case,
Oh, but I thought that one is chapter 6.
we are not looking into detail. We are looking at conservation energy. That's all.
Oh, chapter 6 is independent.
Chapter 6 is deformation. Force causes extension or compression,
Okay.
not energy.
Okay.
How does kinetic energy displacement time graph look like when dropping an object? Right? Initially, when you drop the object, the potential energy is maximum. As the potential energy decreases with height, kinetic energy increases with speed. So total energy equals kinetic energy plus potential energy plus work done against friction. Right? Should be able to write down the equation. Work done against friction at any height equals to total energy minus potential energy at that height minus kinetic energy at that height. Work done against friction appears as internal energy of the air molecules and finally lost as thermal energy. The air become warm. Okay, next part we want to draw the graph of potential energy and height. Height above ground, that's potential energy. Right? MGH depends on height above the ground, and then kinetic depends on speed of the object. So if we throw the object up, then the potential energy is increasing all the time, while kinetic energy is decreasing. Or if we drop an object, right, you can see, we can know that it's going to be a straight line. Mg is constant, h is linear. Right? If we drop an object, then it's the other way around. Initially, it has high potential energy. It goes down to low potential energy to 0 at ground lor. Right? I don't think I want to go over with you all this formula, but it will just confuse you lah. Right? You can use formula to justify the equation, but that's the total energy graph. That's the kinetic energy graph. Right? We are looking at a distance from maximum height. When you drop a ball, the distance is from maximum height. Potential energy is largest. It decreases. So kinetic energy is increasing. This is provided there is no air resistance. But what happens if there's air resistance? Right? Potential energy doesn't change. It is still depend on height. Only the kinetic energy doesn't increase all the time. Right? The increase becomes less and less. You can see that until the kinetic energy becomes constant at terminal velocity. It's quite a straight line near, or when we start, air resistance is very low, speed is very low, then it go further and further away from the line where there's no air resistance. And after that, it becomes constant. Okay, where the ball reached terminal velocity. Okay, I think we have completed. Now we can try the question. Any comment before we carry on?
No.
Okay, so this one summarize for you all that we have covered. Draw your own mind map to help you remember what are the things that you need to remember. Draw on a piece of paper, or you want to do the computer. Okay, let's try some question. Okay, what's the answer for this one? What is the total mass lifted?
I put B.
Right? EP is mgh. Potential energy is given. M is what we want to find. Yeah, told to use G as 10. And height is 1.8. The answer is B. Okay with that?
Yes.
If it's holding to a mass above the head, what's the work done? If it's holding there, the mass above his head, what's the work done?
0.
0. No distance move.
Because it's not moving.
It's not moving. It
No
has
distance move.
energy, but no
Okay.
work done. Muscle is doing work because muscle
Okay.
have to hold it, but there's no work done. Downward force due to the weight of the mass, but there's no distance move. Okay, how about this one?
Well, this one I don't know how to do.
Okay, a child slides down a slide. The weight of the child, you are given the weight. The height of the slide, centimeter. The work done against friction is given 1,300 joule. What is the change in potential energy? And what is the final kinetic energy of the child? Final kinetic energy is down here. Okay. Change in potential energy is mgh. Right? Initially is mgh. And finally it will be 0. So mg is the weight, 150 times the height h. So it's 1,750 joule. Conservation energy. Right? You should be able to write down the equation. Loss in potential energy when you move down from the top there to the bottom there. We call it loss in potential energy. Where does it go to? It goes to gain in kinetic energy and also work done against friction. Then put in your value, potential energy, loss, work done against friction, then calculate your kinetic energy. Can?
Wait, okay, can.
Okay, this one more of a memory work. What is the kinetic energy of a person walking? Either you memorize it or you work it out, roughly estimate.
Half mv square.
Objective lah. Half mv square. Person mass roughly 60 kilogram. Or use your own. Speed about 2 meters per second. And calculate out. And see if it's a structured question, they will allow a range of answer lah. This objective, then you see which one is nearest to this value. Okay with that?
Yeah.
Don't bother about this one. You can try it during your free time. Okay, suppose a force of 12 Newton acting at an angle of 60 degrees to the horizontal pulls a pulley on a smooth horizontal surface at distance 8 meters. What's the work done? Can? What's the answer?
Sorry, I haven't do yet.
Okay, can do it now. Just now we cover too fast up. That's why we got plenty of time. Force,
So you use
force and
12 cos
force and
12 cos
distance.
60.
The force.
12 cos 60 times 8.
So it's fx cos theta, cos 60.
Yeah, 48 joules.
You can get 48 means you are right. Fx cos theta or 12 times 8 times cos 60. Try this one. A body of mass 20 kilogram moving with velocity 50 meters per second is brought to rest by a constant force 10 Newton. What's the kinetic energy of the body? Usually they will give you simple mark like that lah. Calculate the kinetic energy of the body lah.
Half mv square.
That's all. We want to make sure you know how to memorize the formula and how to use it. And get the answer. Then now how to calculate the distance move. Right, write down the equation. Work done equals to loss in kinetic energy. Work done is Fx. Kinetic energy is half mv square. So distance move is 225 meters. Can?
Uh, okay.
Try this one. Give you about 5 minutes.
Is this a trick question?
No, no trick
A
question.
is 0, is it?
To be able to calculate, usually Cambridge is very good. They ask you to calculate simple things. Things you are able to calculate. Then they make it difficult and difficult. They are structured the question that way. So there's no trick there. You should be able to calculate.
A 16 joules.
You should be able to calculate the initial kinetic energy. At the cliff top, the body has kinetic energy and potential energy. So total energy is kinetic energy plus potential energy. At the bottom of the cliff, all the kinetic and potential becomes kinetic energy. That means the kinetic energy becomes the initial total energy lah. So initial kinetic energy is just using the formula, that's all. Half mv square. Put in your value for mass and speed. Get 16 joule. Then kinetic energy at the bottom of the cliff equals to total energy. So it's initial kinetic plus potential. 16 plus potential energy is mgh. Mass is 0.5, g is 9.81, height is 45 meter. Calculate out. Can?
So like 221.
221.
MGH is 221.
Oh, mgh is 21, then minus 16 again, no? Plus 16 again, no? Can?
Okay.
We get 237. Then from kinetic energy, we should know your speed, no? Minus speed. Half mv square. Put in your value. Calculate out. Remember, this is the final speed, but it has a direction. Right? So this is the final velocity rather than speed. Can get?
Wait, I'm still at B.
You got the answer, lah.
Yeah, I got answer for B already. Now doing C.
Okay. So that's the direction. 31 meter per second. Direction. Remember, it has a, even though it's called a speed, we calculate the speed. It's actually a velocity, it has a direction. How to calculate the direction? Oh, that's its direction. We don't know the angle. We know the magnitude. Then the horizontal velocity doesn't change. Still the same. Right? No air resistance. I can draw a picture there. And then complete your triangle or parallelogram. And that's the angle, theta. Cos theta equals to 8 over 31. So theta is 75 degrees. Can? Anything not clear? Yep. What is the problem?
Oh yeah, can.
Can, That's how we calculate our direction, lah. Try this one. Body of mass 0.8 kilogram. Move with constant speed of 12 meter per second. Up a rough plane of length 20 meter. The plane is inclined 30 degrees to the horizontal. The applied force is 10 Newton. Write down the work energy equation.
What work energy equation?
The equation of conservation energy equation. Can. Work done by applied force. Right?
Okay.
What to it? Gain in potential energy, and there's work done against friction. You have to at constant speed, so the kinetic energy doesn't change. That's the equation you have to write to solve this, the whole of this question. Kinetic energy should be able to calculate. Right? That's the formula. Work energy equation. And kinetic energy should be able to calculate. So from that equation, you can calculate your work done against friction. No? From the equation in A, can.
Yes.
Potential energy, C, potential energy is mgh. Right? The slope is 20 meter. The slope is at an angle of 30 degrees horizontal. So this one is further away. Further away is 20 sine 30. I'll work it out. Right? 20 sine 30. So that's the potential energy. Stop me if I'm going too fast.
Wait.
Anything not clear? Your potential energy, then you can calculate your work done against friction. No?
Well, you can just straight away use 12 square. Don't need to use 12.
12 square is
Just
a,
straight away use 12 square only for the velocity.
the initial speed is 12. So that's why we use 12 square here.
Oh,
This is just to give you the free mark. See whether you know how to use,
okay.
how to remember the kinetic energy formula. Then how to calculate the potential energy formula. 1 mark. Then put into the equation. No? And this is converted into internal energy. No? Work done against friction. Same answer. Yep. Anything that you are not sure, you want to ask question. Okay. Okay or not? Yeah,
Wait
okay.
first.
Yeah, okay, let me know. Anything not clear, you ask, I will answer you.
Okay.
Okay. Um, do you have question from last week to ask? Any question?
Don't have yet.
Don't have yet, huh? Let me see what are the question that we can try out.
Oh, finish all already, is it?
Almost we've covered already. Now it's solving question, solving problem.
Oh. Do you think the deformation is a short chapter?
Deformation, I have to check through how it will take one lesson, or today I didn't expect it to be so fast.
Oh, one.
I thought,
Oh, okay.
and that's why I told you, you may have to stay back another 10 to 20 minutes. So, but I didn't realize that I covered so fast with you. You can try this question. We can start deformation if you want, if we still have time.
Sure.
Okay, try this question. And then after that, now another one more. If we still got time, then we will start with deformation.
My teacher is teaching chapter 9 right now.
Chapter 9 is waves.
Electricity.
Oh, yeah. Usually we will try to cover most of AS. And then next semester they will do A2 lor.
Yeah.
Then when you come to near the exam time, they will revise with you lor. Okay, try number
But what's
16.
the formula again?
Power output over power input times 100% is
Output over input.
efficiency lor. Right? Efficiency is power output over power input times 100%. Put in whatever is given, 40% is given. Power output is 100 megawatt. And power input, don't have to change the unit. The answer is going to be megawatt times 100%. So simplify it. Okay, can? Then conservation energy, power input equals power output plus power wasted. Power wasted is 2,500 megawatt minus 1,000 megawatt is 1,500 megawatt. Okay, we got slightly more than 9 minutes. Can or not? Can get the answer? Anything not clear, ask me, I will explain to you. Just playing with the formula, that's all. Anything that you need to me to explain further? Here we cross multiply only. Take the P in to the left hand side, take the 40 down. That's why we get it here.
Oh, okay.
Okay, let's go to the next question. This one. A bicycle dynamo is started at time 0. The total energy transformed by the dynamo during the first 5 seconds increases as shown in the graph. What is the maximum power generated at any instant during the first 5 seconds? So how are you going to solve this question?
Uh, maximum power, so area.
No, not area. Gradient,
Hey,
gradient.
but I thought work done is area.
We want to calculate maximum power. So power is energy divided by time. So it's
Oh,
gradient.
yeah, shit. Okay.
Energy divided by time is gradient, no? Maximum value. It's actually calculus, but they don't want you to know about rate. So it's maximum gradient, no? Can. Maximum gradient.
Oh, yeah.
So, all right, I'll let you do the rest of the question. And then we can start a bit of deformation, no? Now. Okay or not?
Okay.
Okay, let's start deformation then. Okay, let's make a start. Deformation. Topic 6. This one tell you, summarize for you lah. What are the topics you're going to cover for AS? 11 topics you are supposed to study. So topic 9 is electricity lah. So you still got 2 more topics, 10 and 11.
Oh,
Okay or not?
yeah.
Okay. Deformation of solid. We'll look at 6.1, stress and strain. Deformation means change in length. Then elastic and plastic behavior. Here we are looking at force causes deformation. So we look at spring and spring constant. That's the formula where we will encounter. And then that's work done by the spring in series and spring in parallel. Then we define stress, strain, definition of stress and definition of strain. And then we look at the graph. Then force on different material. Right? Summarize for you. Brittle material, ductile material, and polymer. Page 149. Right, that's summarize for you what we have done so far. Okay, that's the syllabus. Importance. Why is it so important, this topic? Solid change their shape under the action of forces. This change may be large in the case of spring, right? The extension can be very large by a small force, or hardly noticeable in some structures such as building. Wire, we try to stretch the wire, very little change only. Study of deformation of solid is an important aspect of engineering. This topic provides an introduction to both elastic and plastic deformation of material. Okay. Forces causes change in length. Okay, you should be able to differentiate what is tension. Deformation is change in length. That is what we are interested in. Tension is the length of the material. In tension, the length of material increases. That's the first case where you stretch it is called tension. The force is called tension. Whereas the second case B is compression, where the two forces compress on the solid, decrease in length. And then where the force is applied sideways on the surface, then we call that shear. We are not interested in the case of C. We are interested in A and B only. So we are looking at deformation, change in length. Right? So in a beam, it will be horizontal, but when we add a heavy load there, it's going to bend. Right? So you should be able to see the arrow. The arrow is going out, so this is tension. Arrow is going in, so this is compression. The same as bridges, right? Where the arrow are coming together, there's compression. This one is stretching, extension, right? Or stretching. This part is compression. Same with a cable bridge. Hooke's law. There's a stretching force. That's the extension. Hooke's law states that the extension of a spring is directly proportional to the applied force, provided the elastic limit is not exceeded. Right? There's a point called elastic limit. After the elastic limit, the spring does not return to its original length anymore. Right? I think this one make a mistake. This is called proportional limit rather than elastic limit. This diagram is taken from the internet. Right? This is supposed to be proportional limit. Elastic limit is after that, where the curved part there. We call it permanently deformed. Mathematically, F equals to Kx. Compare with the equation of straight line, y equals mx. K is the gradient of the